Hi everyone, and welcome to our video on factoring the difference of two perfect squares. Let's focus in on that title, maybe highlight it. We've been factoring. Let's see, we factored by the GCF. We factored trinomials of the form ax squared plus bx plus c when a is 1. And now we're going to try yet another style of factoring. And it's called this, the difference of two perfect squares. So I started off right here with the rule. So I'm going to highlight over that as well, and then I'm going to show you how it works. So if you have a polynomial in the form a squared minus b squared, where a and b are constants, they're just numbers, or they actually, I shouldn't say that. Let me retract that statement. They could be constants, but they of course could also be letters, variables. So variables or constants, and you're trying to factor a squared minus b squared, it will factor always into a plus b times a minus b. Again, let's remind ourselves, the definition of factoring is to write a polynomial as a product, here it is, this times this, of other polynomials. So you'll see that some of the things I taught you in the last video, you can apply here as well. So let's look at example 1. It says factor x squared minus 9. Okay, first we're going to just do it. We're going to do it the way we factored earlier in the course, and then we'll bring it back to the rule up above. So really what we're saying is if we're going to factor x squared minus 9, we have to sort of unwrap and go backwards on distribution. So let me just set up two parentheses. This is my product of two polynomials, which is the definition of factoring. And I see this x squared. So I'm kind of thinking right off the bat, and I hope you are too, like if I put an x with an x, when I distribute, there's my x squared, which I'm so used to getting when I do distribution when I'm multiplying. Okay. Now, if I think about the number here, -9, that's in the back, it to me looks reminiscent of this. Let me write this down. So we just got done factoring polynomials of this style when the a was equal to 1. And if you look, we have an a equal to 1. So this guy is sort of check marked. And we have a c, which in this case is a -9, that's our constant. What's missing here is this bx term. It's like, where the heck is the bx? Well, I guess it goes away. So we've got to figure out something that when we multiply here, like we always do, and combine like terms with this product, it's going to cancel out. And we've seen these before. In the last chapter, that sometimes happens. And then we need to get that -9 here when we multiply here. So again, I'm just thinking out loud here. I'm thinking, okay, the middle term is missing, the bx is missing. So when I combine my like terms, they have to drop out, but I also have to be able to multiply to -9. So in a way, going off the language of the last video, my two numbers that I choose need to multiply to be -9, but they must add to be 0. They got to drop out. So two numbers that when I multiply them, I get a -9, and when I add them, I get 0. So I hope you're thinking what I'm thinking. I'm thinking 3 times -3 multiplies to -9, 3 plus -3, 0. And there it is. So I'm going to put a +3 and a -3. Now let me check that. If I check it and I do the full check, it's going to look like this. X times x, x squared, x times -3, -3x, 3 times x, +3x, 3 times -3, -9. Here they go. -3x plus 3x drops out to 0, and I'm left with x squared minus 9, which is exactly what I started with. Now let's see how this plays into the rule. Let's take a look here. So here's the rule. Now let's break x squared minus 9 down into the difference of two perfect squares. So the way I would write this under here would be like this. So I've got an x squared, that's my x squared, minus 9 can be written as 3 squared. That still means x squared minus 9. Now, once I get there, here's my a, here's my b. So the factored result is supposed to be a plus b, a minus b. And that's the exact same answer we got when we sort of thought it through. The rule here is nice, it's quick, it's easy and painless, but let's just not forget what's really going on to create the rule. Okay, so let's take a look at the next example. Factor x squared minus 36. So again, you definitely see that x to the second power minus, how could I rewrite 36 as a constant to the second power? Well, 36 is 6 to the second power. So there's my x squared minus 36. So here is my a, and here is my b. So I know that, according to the rule up top, my factored answer is going to be x, or a plus b times a minus b. If I check it, I can see I've got x squared minus 6x plus 6x minus 36. There they go. Negative 6x, positive 6x, cancel out, and I'm left with x squared minus 36, which is what I started with. So I know it's a good answer right here. Again, I needed two numbers. If you go old school, I needed two numbers that multiplied to give me a negative 36, but added to give me 0. And those two numbers are 6 and negative 6. So it works out. Okay, let's take a look at example 3. Factor 9x squared minus 100. So we have to see if this is truly the difference of two perfect squares. It's definitely the difference. So there is this element of subtraction, which is good. But now I have to ask myself, what monomial, when I square it, gives me 9x squared? And what constant, when I square it, gives me 100? So you can pause and think about it. What it will be is 3x squared makes 9x squared. And that's because 3x times itself, which is what squaring means, gives you back 9x squared. 100, that would be 10. So here's my a, and here is my b. So my final answer, factored form, a plus b, a minus b. Let's check it. Okay, 3x times 3x. There's my 9x squared. 3x times negative 10 is negative 30x. 10 times 3x, positive 30x. 10 times negative 10, negative 100. These cancel right here. And so I'm left with 9x squared minus 100, which is what I started with. That's how you always know that you did it correctly. Okay? And here's my last one. Difference. So we got that. Always looking for that minus sign of two perfect squares, perhaps. Let's see if it truly is. We've got to figure out what raised to the second power makes 25a squared, and what raised to the second power makes 64b squared. So here I'm thinking 5a, and here I'm thinking 8b. I can check that. 5a times 5a definitely makes 25a squared, and 8b times 8b definitely makes 64b squared. Okay, so I've got a here and b. So my final answer should be factored form 5a plus 8b, 5a minus 8b. My check, 5a times 5a, 25a squared. 5a times negative 8b is negative 40ab. 8b times 5a is positive 40ab. 8b times negative 8b is negative 64b squared. Negative 40ab plus 40ab cancels, leaving me with 25a to the second minus 64b to the second. Final answer, what I started with. Okay, so you start to sense a pattern here, and that pattern always goes back to this little rule. Now, before we leave this video, there's one last thing I want to do, and this is a common mistake I've seen over the years, so I'm going to flip this over. Students will often see a problem like this. Like, let me just make this up. Let's say it's x squared plus 16, okay? And at first glance, they see the x squared, okay? They see the x squared, and they see 16 as 4 squared. So right away, they're like, okay, so here's my a, here's my b, and so my final answer must be x plus 4, x minus 4. They circle that, and they walk away. What they did not pay attention to is this sign right here. It turns out this isn't right. This isn't true. What will happen is it'll look like it's going to be true, but watch what happens when I check. Here's your x squared. Here is the negative 4x added to the 4x. So there's how you're going to drop the middle. So everything's checking out. But when you take the last times the last here, you're going to get negative 16. Right there. Negative 16. Now, this is always going to happen when you are multiplying two binomials that are exactly the same but have opposite signs. Let me give you a vocab lesson here. When you have two binomials that differ only by the middle sign, these are called conjugates. That's just food for thought there. So when you're multiplying two conjugates, the like terms will always drop out, but in order to have them drop out, one has to be negative and one has to be positive. Well, if one has to be positive and one has to be negative to make this happen, then when you multiply them together, this will always be a minus. It can never be a plus. So it turns out that the sum of two perfect squares, non-factorable. It just won't work out. There's nothing you can break this down to. There's no product of polynomials that you can break x squared plus 16 down to and have it multiply back to x squared plus 16. Students have said, oh, well, then maybe it's just two pluses, x plus 4, x plus 4. No, because that is x squared plus 4x plus 4x plus 16. So now you have the x squared and the positive 16, but you also got yourself an 8x. And this doesn't have an 8x. So just be very mindful when you're factoring that you are looking at the difference, that means subtract, of two perfect squares. All right, thanks for watching.